Hello everyone, welcome to this video. In this video, we'll be talking about normal subgroup test. So in the previous video, we already saw what is the definition for normal subgroup, right? What was it? For a subgroup to be a normal subgroup, its left coset would be equal to right coset for all the elements of the given group, right? So now in various situations, what we need to do, we need to verify that a given subgroup that is normal or not. We need to check it. So by definition, it would become quite tedious sometimes. So therefore, we require these kind of tests in order to determine that quickly. So what is that test? We first of all have a look at the test. It is the name here is normal subgroup test. The test here tell you that if H is any subgroup of the given group G, right, and if this subgroup that is normal in G, right, this would happen if and only if for all the elements X in the given group G, we have this thing that X into the subgroup into X inverse that is contained in the subgroup. This is the condition and this is the test. So let's first of all prove this, and then we'll be looking at its application. How can we apply it? So for the proof here, we first of all assume that if H is any normal subgroup in G, right, then we know that its left coset, suppose we take some element X in G, so corresponding to this element X, taking it as the coset representative, we can write it like this. We have the left coset equal to the right coset. So that means if we take some small h from this capital H and some small h dash from this capital H subgroup, in that case xh would be equal to h dash x, right? So this is the thing. Now using this thing over here, what we can do, we can post multiplying on both sides of this equation by x inverse. So you would have x inverse here, you would have x inverse here. This and this would club together and give you identity. Some element into identity is that element itself. So you have your result. So this is what you have here. And this is what we wanted to prove for this part. Now because this is a member of the subgroup, this is also a member of the subgroup, so that means, and these were the arbitrary elements, so that means this relation is true for all the elements of H. Hence in general we can write that small x into capital H into small x inverse is contained in capital H. So this proves one part of the proof. Now because we have if and only if condition here, so that means we also have to prove the converse. For the converse, we assume that this condition is true and we prove that the given subgroup is normal subgroup in G. For that, we suppose that X inverse is contained in H for all X which are member of the given group G, right? For proving H to be a normal subgroup in G, we need to prove that the left coset is equal to the right coset. For that, if we suppose within this condition that because we are taking this X from the given group G, G contains all those elements which are also present in H, right? Because H is a subgroup of G. Now, if we take some element A in H, so this element A would also be present in G, so we can let X is equal to A, there is no issue. So if we first of all are taking X is equal to A, where A is also some arbitrary member, right? Once we change this member, we have all the members of the group. You can substitute any member of the group in place of A. So A acts as a dummy member. Okay. So here if you substitute in place of X the value A, you have A inverse contained in H, right? So post multiplying both sides by A, what do you have? You have A here and A here, right? So it would become, this thing would become identity, and so you have AH is equal to, contained in HA. Let's mark this as equation 1. Now, if you take X to be A inverse, now A inverse would definitely, because A is present in G, then A inverse is also present in G being because it's a group. Now, if we take this X to be A inverse, we would have this relation. If we substitute it here, within this expression, it would be A inverse H. inverse of A inverse. And what would be the inverse of A inverse? It is just A, right? So you have this relation, and now we can pre-multiply both sides with A so that this thing would become identity. So you have HA contained in AH, right? So you have HA contained in AH. So combining equation number 1 and equation number 2, we have the result that AH is equal to HA. That means for any member A, which is a member of G, taking this to be the coset representative, the left coset is equal to the right coset. And this thing is true for all the members of G because A was taken to be an arbitrary member. Hence, H is a normal subgroup of the group G. Right? So this is the proof of this result. Now let's have a look at its application. So for an application, I am considering the group to be the general linear group having order 2 cross, it consists of all 2 cross 2 matrices whose entries are taken from the set of real numbers, right? And whose determinants has to be non-zero. Now let's take SL 2, R special linear group of 2 cross 2 matrices with real entries to be its subgroup. You know that all the members in this group have the determinant 1 in particular. So we say SL 2, R, that is a normal subgroup of this group. How? We can see this thing using the normal subgroup test. So let's consider our group G, the given group to be written by the symbol capital G and the given subgroup to be written by the by the letter capital H, right? Now, if we take some member from the given group, it should be a matrix. So let's denote it by capital A. Capital A is a member of the given group G. Capital B is a member of the given subgroup H. Right? Now, because the subgroup is special linear group, so it's any element taken from it would have determinant equal to 1. So the determinant of B has to be equal to 1. Now, because we wanted to prove that or verify that it is a normal subgroup, we need to see that if we take any member from G, which we have taken to be A, right? So A multiplied with the subgroup multiplied with its inverse, it should be contained in H. So that means we have to take some element of this kind and it should be present in this subgroup, right? So I am considering A, B, A inverse, where A has been taken from G, right? B has been taken from H, and this is again from G. So this not G inverse, the element is A inverse. It is also present in G, right? So let's consider its determinant. When will it be present in the subgroup? Whenever we have the determinant of any matrix, 2 cross 2 matrix with real entries as equal to 1. So let's see what is the determinant. If the determinant appears to be 1, we would have this particular element present in the given subgroup. So let's solve this one. So determinant of this thing would be equal to determinant of A, determinant of B into determinant of A inverse, right? How this is there? This is using the properties of determinants. Now, because B was a member of the special linear group, right? So its determinant is obviously 1. So using this thing here, its determinant is equal to 1. So we are left with determinant of A multiplied with determinant of A inverse. So you can write this thing as 1 divided by determinant of A. So both of them cancels and we are left with the number 1. So we have the determinant as equal to 1. So therefore, whatever is this member, it should be present in our subgroup. And what is that subgroup? It is special linear group consisting of all the 2 cross 2 matrices having real entries and having determinant as equal to 1. And so therefore, because this is true for all the members A taken from the group G, because A was an arbitrary member, therefore we have this result. Hence, by the normal subgroup test, we can now clearly say that this special linear group is a normal subgroup of the general linear group. So I hope you understood this test well. Well, that is it for this video. Thank you for watching.